Very good morning. In the last lecture, we had a introduction about finite difference approximations to parabolic PDEs, and also we have discussed implicit method. Okay. So, that means considering the time levels to compute the values at a particular time level, we need the data at the past time level, and further the values at the next time level are obtained explicitly in terms of the past time levels. Okay. So, today let us see about implicit nature of finite difference approximations for parabolic PDEs. Still we are considering the heat conduction equation. Okay. So, that is the reason I kept the title as implicit methods for parabolic PDEs. So, we consider the heat conduction equation. Okay. So, now in order to obtain in the last we for explicit we made central and then this is forward. So, now what we do is backward for this and central for this. Okay. So, accordingly we obtain now when you approximate backward, there is non-zero leading coefficient starts at k, and when you approximate central this starts at. Okay. So, I am not talking about this right now because we learn about this in detail in the coming lectures. Okay. So, now even though we have written see for example, this is backward, right, j minus 1, but for convenience what we do for convenience, let us write down the same formula at j plus 1. Okay. Because this formula contains j and j minus 1, but it is a general notion that we represent using j plus 1 and j. So, it is just a convenience. Okay. So, let us write down this at level j plus 1. Okay. So, writing the above approximation at level j plus 1, we get so that means j plus 1, that means j minus 1 will be j. You can see. Okay. So, now you can see two levels involved, j plus 1 and j. Okay. So, this can be simplified. So, lambda is our grid parameter. Okay. So, left hand side you have terms at level j plus 1, right hand side we have terms at level j. Okay. So, this is in some sense two levels involved, but more terms of level above. So, this is an important remark, more terms of level above than the level below. So, this is an important remark. So, this shows the implicit nature of the scheme. Okay. So, how this is going to give us the implicit nature. Okay. So, let us have a look. So, the formula we have okay. So, which means suppose this is u I j. Okay. Yeah. So, it is so this is in contrast to the explicit scheme which we have derived in the last lecture. You can see more terms at level j plus 1 compared to the level below. Okay. So, how this is going to bring up the implicit nature, we will see. So, this corresponds to say t equals 0 and this is nothing but j equals 0, then when t is delta t, j is 1. Okay. So, let us run through it with a specific case, then see how the implicit nature comes into picture. Okay. So, we need the equation again. This is the equation u I minus 1 okay. Now, for example, let us say, so this is t. Okay. So, if you see, let us say these are the boundaries. Okay. So, this is x 0, this is x 1, x 2, x 3 and x 4. So, this is our boundary and this is our boundary. Okay. So, essentially we need to solve at the internal grid points. These are the internal grid points, because these boundary points we know the solution. Okay. So, now let us run the solution at consider j equals to 0. So, what we get 1, 1, 1. Okay. So, this is our equation if you consider j is 0. So, that means in this expression we know only u I 0 values, okay, because these are at higher time level. So, now still we have to realize the implicit nature. Okay. So, now we start what will be the first value of I for which we can run this equation. See, because of this term, if you put I equals to 0, so you get u minus 1, which is outside. Okay. So, therefore, the first value of I for which we run the equation is I equals to 1. Okay. So, let us run this equation for I equals to 1. So, the equation we have for j equals to 0 okay. Now, if you run the equation for I equal to 1, okay. So, what is this doing? What is this doing? So, u 0 1, okay. So, this is x 0, x 1, x 2, x 3 say. So, u 0 1 will be this, then u 1 1, u 2 1. Okay. So, this is connecting, okay. So, this is connecting, right. So, that means out of 4 quantities you know only this value, you do not you know this value. So, these two are the unknowns involved in this equation. So, what are the unknowns? So, these are the unknowns. Okay. So, now let us run the equation at I equals to 2. So, then we get and here what are the unknowns? And assuming this is boundary in this case. So, u 3 1, this is u 3 1. So, this should be known quantity. Okay. So, now I 3. Okay. So, if you run I 1, I 2, I 3 is on the boundary. So, this will introduce fictitious values. So, we do not go for I equals to 3, right. So, what happened in this case? We get one equation where you have two unknowns, in second equation we have two unknowns, and this is known. So, let us give some other color. So, this is known quantity, this is known quantity, and this should be known, this should be known. So, two equations and two unknowns. Okay. So, if you can see the implicit nature of this scheme is visible, because it involves two time levels, one is j and j plus 1, of course, in a explicit method also the same. However, in the explicit method you have one quantity at level above and you have more quantities at level below to the right hand side. So, for each value of time step you get explicitly the values, okay, at each nodal point. However, in the implicit what happened? We have seen we get a system of equations. So, how do we get system of equations? Because we have more quantities at level above than level below. Okay. So, this brings implicit nature of the scheme. Okay. So, let us see in detail. Okay. So, I would like to explain with more in detail. suppose these are the boundary points. So, first time when you run, so these are the 3 points connected to this point, and we get equation 1. Okay. So, next time when we run the equation, so this is another boundary point, this is another boundary point. Okay. So, then this is another grid point, let us say. So, then next time, okay, then what will happen for these, you get equation 2. Okay. Then next time, these 3 points are connected and you get equation 3. Okay. So, we march past along the nodal points in this. So, we get an equation, however, one boundary point is removed, 2 at end points you have 2 unknowns, this and this, whereas in the second equation you have all 3 unknowns. Then we do like this. So, if we do continue like this, at the boundary point, what we will have this and this. So, they will be connected with. So, here this is a known and here this is known. So, at the equations where we run corresponding to I equals to 1 and corresponding to I equals to n minus 1, we get one known quantity here and one known quantity. So, the remaining, so this forms implicit and this is nothing but system of equations. Okay. So, let us see with an example. Okay. Let us see with an example. So, let us consider the example. Okay. So, the same example which we took in the last lecture. Okay. And so, this is so 0 and 1. So, this is 1 by 3, then this is 2 by 3. Okay. So, this is x 0, x 1, x 2, x 3. Okay. So, now we want to run the scheme. So, the unknown points in the internal grid points are these 2. Okay. So, let us consider the formula. Okay. Right. So, consider the case where we have lambda equals to 1 by 4. Okay. So, now j equals to 0. J equals to 0. So, this is 1, okay. So, this we are going to run I equals to 1 and I equals to 2. Okay. So, corresponding to I equal to 1, we get okay, and corresponding to I equals to 2, okay. So, now if we use the values of lambda, the system becomes so lambda is 1 by 4. So, this is okay. Now, let us identify the unknowns. So, these are the unknowns and so these are the known quantities. Okay. So, then solve for u11 and u21. Okay. So, this is a this can be done very easily by substituting the corresponding values. Okay. So, we have seen both explicit and implicit methods for the parabolic PDE. Okay. So, the explicit and implicit nature is coming because of the discretization corresponding to the time levels. Okay. So, for example, if you do forward, we have seen forward with respect to time, we have seen we obtain explicit, whereas if you use backward, we obtain implicit. Okay. So, now I have been postponing to address one of the issues. What is that? The issue is when you approximate a given PDE with a suitable finite difference scheme, you are throwing away terms from certain order, right. So, what is this, and then how do we conclude that whatever we have thrown is up to this order, and what is this called? Okay. So, definitely you are true, this is called local truncation error, because when you approximate any particular scheme, for example, forward time when you have done it, what is happening? The difference and then the non-zero leading coefficient, if you consider, that is a multiple of k, that is delta t. Okay. So, that means it is a first order, okay. Whereas, if you use a second order derivative approximation with central, you are getting leading non-zero coefficient is order of h square, that is order of delta x square. Okay. So, that means this is a second order with respect to space. So, now combining this, you have order of k plus h square. So, that means the error term is of this order. Okay. So, our next aim is to study about local truncation error in detail. Okay. So, let us talk about this. So, while discussing numerical solutions of ODE, we talked about local truncation error. Okay. So, now again the equation we consider still the same. Okay. So, now let us say this has been approximated by Fiju equals to 0. Okay. So, that means this is the approximated operator. Okay. So, this is the original operator and this is the approximated operator. So, in some sense LU equals to 0 has been approximated by Lij u equals to 0. Okay. So, I have given Fiju. Okay. Now, let us say u bar be the exact solution. U bar be the exact solution, right. So, then what do you expect? Exact solution satisfies this, but when you substitute exact solution in the discretized version, the approximated version, we are not sure whether this will be exactly 0. Okay. So, the remark is Lij u is approximately 0. Okay. This is approximately 0, right. So, that means this implies Lu minus Lij u should be approximately 0, which we call Tij. So, this is our local truncation error. Okay, right. So, let us see what will happen. Okay. How do we compute? Okay. So, we are going to compute. So, our Lij u is, so consider the explicit scheme. So, we are considering the explicit scheme. Okay. So, now this is approximately 0. Okay. So, now let us so whatever I have mentioned, we are going to realize that. What is that? Earlier we were mentioning this is order of k and this is order of h square. So, now we are trying to realize that indeed the error which is involved in this approximation is in this order. Okay. So, how do we do that? By Taylor's expansion. Okay. So, consider, so the error is nothing but you replace by the true, okay, in the discretized version. So, that is what I am going to do. You take the discretized version and replace the true value. Okay. So, I have considered the discretized version and replaced by the true value, that is u bar. So, therefore, this should be the error. Okay. So, now we go for expansion as follows: u bar I plus 1 j is equal to, this is nothing but u bar of x I plus 1 d j. Okay. So, if we expand, so I am using h notation instead of delta x. So, h of course, this is evaluated at plus h square by 2 factorial, this is evaluated at d j. Okay. Similarly, this is not component, this we can keep it as x actually, indeed. This you can leave it as x I or x, because we are writing this notation. Okay. Okay. So, u I plus 1 we have computed, I minus 1, and we have with j plus 1. So, better we write this term as well. So, this is with k and the derivative is with the t. Okay. So, I am not writing the third term, we can write it because we may use it later on. So, I hope you can see. So, this is by 6, okay, and here with a minus sign, and here so plus dot dot. Okay. So, now all this we substitute in this. Okay. So, let us substitute, then we get T I j is equal to. So, let us write down the scheme, so that we do not make any mistake. Okay. So, this is the scheme. So, now we have to substitute the Taylor series expansion, which we have done previously. So, therefore, this reduces to, so I keep 1 over k here. Okay. Then j plus 1, this is u bar. So, I am not writing evaluated at x I t j, okay, that is understood, please. Then the next term will be k okay, okay, then okay, then u bar I j. So, this is we write it minus u bar. Okay. So, this because there is no expansion u bar. So, I have already mentioned this is a evaluation at Xij. If you want here you can write down for all the terms. Okay. Now, minus 1 over h square u I minus 1 j. This will be u bar minus h plus h square by 2 minus so it is a little lengthy algebra, but we enjoy at the end of it. Okay. So, this is plus I am going one more term. So, this is dot dot, then minus 2 u bar, then the next term plus u bar plus h everything evaluated at. Okay. So, now let us see what is going to happen. So, we have this term cancels with this term. Okay. Then we have this cancel. Okay. Then if we look at here, these are the only terms which with respect to time derivatives. Okay. So, nothing from here may get cancelled, the first observation, first look, but later on when we use the equation there may be some tricks can be done. Okay. So, but before we do that, let us see the straightforward terms. So, these are straightforward. So, then this term goes away with this term. Okay. So, the first term which we are going to get, see k gets over, then this is the first term we are going to get, and from here you see h square by 2. So, h square by 2. So, we get h square dou square u bar by dou x square, then h square also get cancelled. So, the first term which we are going to get is dou u bar by dou t minus dou square u bar by dou x square. Okay. So, this is the first term. So, let us write down. So, T I j reduces to of course, evaluated x I T j. Then, so to have a remark, so this is done. Okay. This is done, this is done. Okay. So, now what is the next term? As I mentioned, time derivative is only in this. Okay. So, maybe let us put down the next term, this one. Okay. So, I am putting a tick. So, k square by 2 dou square u bar by dou t square. So, let us write down the next term plus. So, it is not k square because there is one k there. So, it is k by 2 okay. So, this is done. Then these terms again get cancelled, cube terms. Okay. So, they get cancel. So, the next term we have in hand. So, this is this term with a negative sign and a h square goes off. So, I am putting a tick. Okay. So, next term we are going to put down is these two, right. So, h square goes off and this is twice of it. So, the next term will be minus h square by 12 okay. Now, next term k goes off. So, I am going to put down this. Okay. So, the next term I am going to put okay. Then what would happen to the h 5 coefficient here? H 5 would get cancelled. So, the next term should have been h 5. So, that get cancelled. So, what is the next term? So, the next term here h 6 okay. And here also h 6 okay. So, h 6 by something okay. So, that get cancelled, h square get cancelled. So, h 4 remain with the corresponding coefficient twice of it. Okay. So, let me put down that. So, the next term minus okay. So, we have written terms up to this T 4, the next term is T 4. So, I did not write down the T 4 okay. Right. So, this is what. So, now let us observe closely what is the this combination. Having observed that u bar is exact solution, u bar is exact solution. Okay. So, what is this? Since u bar is the exact solution of okay, we have this box equal to 0 okay, obviously. So, therefore, what will happen? The leading non-zero term, the same is called principal part of the local truncation error is leading non-zero, because this becomes 0. So, now leading is coming from here. Okay. So, this becomes this is a leading term. So, let us observe this carefully. So, T I j reduces to, so I am putting k there, half minus h square here evaluated at xitj. Okay. Then we have remaining terms. Okay. Now, this quantity so when we evaluate at this, they reduce to some specific value. So, the lead term becomes some C 1 k plus C 2 h square, okay, assuming this is C 1 and C 2. So, this is nothing but okay, in this order. So, this is the local truncation error which we have seen. So, since this is a leading order, we say, so therefore, T I j is this is what we have realized. Okay. So, this is what we have been writing when we have discretized. Okay. So, now having obtained this error, definitely our aim is to reduce the error, to minimize the error as much as you can. Okay. So, here in this case we have obtained non-zero leading term, okay, and then we have computed the estimate on that, and we declare that the local truncation error is of this order. Okay. But however, we are interested in minimizing the error as much as you can. So, this is what you should look for in general for any numerical method, okay, in general. So, now in this case is there a possibility to reduce the error further? Okay. So, let us observe closely and see whether there is a possibility. Okay. So, if you observe closely, if this term is 0 somehow, okay, so then we can realize the next non-zero term will be this. Okay. So, where you have a k square and h 4. So, that means you are going to minimize. Okay. So, the question is, can we minimize the error further? So, can we minimize the error further? So, in this case at least the answer is yes, in this case. Okay. How? Let us see. So, if you consider our T I j, okay. So, this is k times half okay, we have this, right. So, this particular term is order of k square h 4. So, this you can write plus order of, okay. So, you can write now. Let us play a trick. So, the trick is we have dou by dou t equal to, because this is from our equation, right. Hope you are, this is just our equation with a dot, where dot is u. So, now consider so this is nothing but, see, 1 dou by dou t is square of it, okay. Right hand side already you have now, this is nothing but this is nothing but, okay. So, this term is equal to this term, right. So, therefore, T I j becomes k by 2 minus h square by 12, you can plus order okay. Hope you are able to follow, right. This is the trick we did. Then this term I am writing, I have taken substituted for this term, I have substituted this and taken common, and this is the next non-zero term. Okay. So, now force this to be 0. Okay. So, this is 0 if 6 k by h square equal to 1. Okay. So, in other words, T I j is of order k squared plus h 4 for k equals to h square by 6. That means, if you choose your discretization such that k is h square by 6, so then we improve, because the next non-zero it has gone one step further, right. So, the error is getting minimized. Okay. So, therefore, there is an improvement. Okay. So, when you discretize, you should make sure that this choice of step size is chosen such that the error is minimized. So, now this depends on the method, this depends on the corresponding approximation, and for sometimes we may not be able to get exactly this kind of scenario. So, there you have to use your intuition and then come up with some other technique. Okay. So, what we have learned so far is we have learned explicit, implicit methods for parabolic PDE. In particular, we have considered the heat conduction equation and how to compute the local truncation error, estimate on the local truncation error. Okay. So, now there are serious concerns about these approximations. Okay. So, these concerns we will discuss in the coming lectures. Until then, bye.